Okay, so we are going to be looking at post-processing, but really a lot of this stuff happens at the very beginning as well. So, the terms, as I was trying to allude to, post-processing, pre-processing, it's in my brain, it's all kind of happening, at different stages. I mean, they call this post-processing, but you'll see a lot of it sounds like some of it could go into pre-processing, but technically it's post-processing. So we have a few things to take a look at. Let me hide this bar here. So we are going to look specifically at what's known as a domain. And there are three different domains. These are essentially different procedures that the computer goes through to try to change an image. So the change can be a lot of different things that we're going to use some examples when we get to each one of these. But basically, any image manipulation that you do, changing the contrast, magnifying the image, increasing the spatial resolution, decreasing the spatial resolution, just about anything that you can think of that we as technologists do, but also it extends to radiologists and it extends to other types of radiological images like CT and MR scans, fall under one or more of these three domains. And you'll see that the terms themselves will make sense, right? And they're pretty good terms. So, spatial, intensity, and frequency. We'll start with spatial, only because this one can be broken up into sort of three subcomponents or three different types of operations. So, spatial domain, think of the word space. This classroom is a space, the college is a space. It has an address, right? Whatever this room number is, I don't even know, across from 300 J Street. So in the spatial domain, everything that you're doing is linked to an address. And that address is where does the pixel live? It's going to live on a particular row and a particular column, each and every thousands of them, based on where it is within that matrix. So all three of these operations, point processing, area processing, and global processing, are dependent on knowing the location of every single pixel, or some of the pixels, right? But whichever you're acting on, it needs to know where they are. So point processing, in particular, is pixel specific, pixel by pixel. And that is tough because the system has to look through thousands of pixels. Remember, there can be over 200,000 pixels in a 512 by 512 matrix. And it happens really quickly. We don't realize how fast it happens. But it still takes some sort of computational time and effort on the side of the computer to do this stuff. Memory locations have to be looked at one at a time, all of that. But for us, it seems pretty quick and simple. So one example, and there can be many examples of all of the different things that we're going to do and talk about today. So I don't want you to say that the only thing that point processing is responsible for doing is subtraction. But subtraction has to be one, or is one good example of how point processing works under the umbrella of the spatial domain. So in this example, you start off with A, and you can't see the vessel very well because it's a dark vessel against a fairly dark gray background. Wouldn't it be nice if we could subtract it out, pull that vessel out so we could see it better? So subtraction, in many cases, will identify the different pixels that make up the vessel, change them to a brighter level, and then when you combine this with another technique known as maximum intensity projection, or MIP, it'll, in addition to that, make the background even darker than just the opposite brightness level. And it can also make the vessel even brighter. So you end up with, what you see here, D, which is, very bright against a dark background. But notice you've lost some of the vasculature there, right? So it might be hiding. So this is an example where you had subtraction, which converts the grayscales from one to the other. At the simplest level, it's white to black, black to white. But remember, every shade of gray has its opposite corresponding shade of gray. And combined with maximum intensity projection, which allows for the background to get even darker and the vessel to get even brighter. And it does this row by row. So that was point processing. Area processing, also under the spatial domain, also based on finding where the pixels are. So it's based on locations of pixels and rows and columns in our matrix, looks at multiple pixels and does an operation on multiple pixels versus one at a time. So a good example of this is magnification. So follow with me here. In image A, you have a circle there that's a region of interest, ROI, if you like, acronyms today. But you can see within that region, there are different brightness levels of different pixels, right? It's probably a little bit brighter, at the tip of the bone, but where the canal is in there is more soft tissue, so it's darker. And imagine that you can count up how many pixels of particular brightness levels are in each one. So now imagine that you take each one of these pixels that's in this circle and take each one and create 10 or 20 of them at the same brightness level. So you take all these pixels here, multiply them by whatever magnification factor that you're looking for, make those the same brightness level, and then you end up with a magnified image in B. And even more so in D. Now, what's interesting here that I'm appreciative of is that it's not a perfect process trying to figure out what pixel brightness is which one and then duplicating them all in just the right way. There's probably some that are right on the border, and how does the computer know which one to pick exactly? It does a pretty good job, but this is one of the rationales for the fact that the magnification causes some distortion and it doesn't look as clear as the original. So it's bigger, but a little fuzzier. Can you tell? Mm-hmm. Right. But sometimes just because it's fuzzy doesn't mean it's bad. Sometimes you're able to see something, and then, in our digital world, a lot of things can be undone. So you make something big, and then you notice something perhaps, and then you go back and make it smaller, which would then do the opposite and sort of increase that spatial resolution a little bit. So you can go back and forth. In fact, you can probably show both of these when you have a very fancy monitor like the radiologists have that allow them to have multiple windows open with different things happening in each one, right? Where we usually have one screen, right? You have one image, one screen, you do one operation. If you want to see something else, you got to, go back and forth. So that's area processing, right? We're looking at where the pixels are and then duplicating some of them. Global processing, as it sounds, is going to affect the entire matrix, the whole world, so to speak. And a good example of this is something that you probably don't think much about. I know I wouldn't, honestly, if I wasn't teaching a course, right? When you flip an image, you just kind of click and it happens, right? But in a sense, what is happening? Again, it's based on rows, columns, and essentially pixel addresses. And you are simply matching one pixel on one side to that opposite column and switching the brightness levels so that essentially what was on the left now is on the right, or what was on the top is now on the bottom. All this happens in milliseconds. You click, it happens. You turn, it happens, right? But you have to imagine that the computer is looking at the entire matrix, knowing exactly where each pixel is and what the corresponding partner pixel might be, and then flipping it. So that would be an example of a global process. Right? And you can combine some of these processes, right? I mean, we flip, and then we, do magnification, or vice versa. So it's not like you can only pick one, right? You can do all these things in different ways. So that was all spatial domain. Second domain is kind of like another way that the computer can process an image. Another way that it will analyze the image would be what's known as the intensity domain. So this is not intensity of radiation, which is what we talk about a lot in this class. This is probably what you have in mind before you started X-ray. So I've tainted you perhaps, but now we're talking about the intensity of light or different brightness levels. So an analysis here is still looking at pixels, but now it's looking at it from a certain perspective of what is your brightness level? What's your brightness level? What's your brightness level? And being able to do things like create the initial histogram, which we said is a map of where are those pixels and what brightness levels do they represent, right? The histogram graph is a bunch of columns that just say each column is a different grayscale. How many pixels fall into that grayscale? So another example where the intensity domain is involved is when you change the brightness level or change the contrast level of the image. So the example here, one of the examples, is where we change the contrast level from something that is longer scale to something a little bit shorter scale. And I noticed today, as I told the class before you guys on the train this morning, that I review the lecture in the morning, and I'm reviewing things and I'm magnifying, because it's hard to see a whole slide on one little phone. But when I looked at this a second time, I noticed these two little drawings here that relate to what we're talking about and relate to what we talked about last week, where the little diagram here, the image of the slope of the contrast curves that we started talking about last week and continue a little bit later, is very steep here. So it goes through the grayscales faster, which creates a shorter scale image. Right? And even the numbers relate, but they're kind of hard to read, even harder. Right? But you can see, even though this looks pretty steep, it's much more shallow than this one here. Right? If it was a hill, you'd rather walk up the hill on the left than the one on the right. Here, I picture, I'm walking through the woods, seeing more stuff, more grayscales. So I get a longer scale of contrast. And last, we have the frequency domain. So this becomes a little bit different. Throw out a lot of that geographic discussion that we were talking about. Now it's all about waves. It's all about trying to identify structures based on the frequencies that are coming out of the system. So when we talk about frequencies, it's helpful to understand what represents high versus low frequencies. So higher frequencies represent smaller, more distinct objects. Larger frequencies are, so it's low frequency, smaller objects, large frequency, larger objects. And In a sense, it still has to kind of look at certain areas within your image. And it is used specifically, well, I shouldn't really say specifically, right? But one of the major uses of analyzing the frequencies of objects is to try to alter a specific object in such a way to give you a better image. Like if you want to look at just sort of the top of the metacarpal, right? And you want to do something known as edge enhancement to make the fine details kind of come out at you a little bit more. That would be an example under the frequency domain. And specifically, that would be known as edge enhancement. And what does that mean? Edge enhancement is going to utilize a high-pass filter, not the kind of filter you find in a tube, not the kind of filter that you can, touch or pour something through. This is a digital filter. And it'll give you a more pixelated image, which might be not good, right? If it's too pixelated, because sometimes it'll get a little bit noisy. But it steps up the spatial resolution. The example here is a high resolution chest algorithm versus standard. And I don't know if you can see it all the way back, because things become less clear the further away you are. And I've influenced myself already by knowing which one is which, because the titles are there, of course. But I hope you can see that the one on the left is a little bit more detailed. The one on the right, a little bit fuzzier, maybe. You would say that the standard algorithm on the right just looks fine. It's just now that you have something to compare it to, right, that you can see that it's more pixelated. Spatial resolution is a little bit higher on the left side. If you look at the line pairs, and we're familiar with this from doing a lot of labs, right, we can see that where you can see those line pairs on the left, top left, you can't see them on the top right. And the idea is that, of course, those represent each of those images' spatial resolution. Yes?
Why does your spatial resolution go up if it gets more pixels?
So that's the trade-off, right? When your spatial resolution goes up, noise goes up too. So it becomes grainier and grainier. Right? So that's a good segue, because if you have an image that's very grainy and you want to reduce some of that spatial resolution, you do the opposite. You do what's known as smoothing. So when you smooth the image, it takes away some of that graininess and generally makes it brighter. And to stick with what we're talking about here, instead of edge enhancement, you would do, like I said, smoothing, but that would actually utilize a low pass filter versus a high pass filter. So edge enhancement increases spatial resolution, goes with high pass filter. You want to get rid of some of that graininess, reduce your spatial resolution. That goes with a term known as smoothing, and that would then go with low pass filter. Yes? So, yeah, that's a good question and tough to answer. So the question is, so what's really happening to the pixels? Well, there's only one thing you can do with pixels. You can only change their grayscale. And you can only, and by doing so, we'll change multiple pixels in a certain location. Smoother images tend to be less detailed, but brighter. And by the way, these are terms we use in CT, in terms we use in MR. So all this digital stuff that we're talking about extends past just radiography, right? It gets used in a lot of different ways. I suppose ultrasound too, but that's not my expertise. Yes?
So the size of the pixel is going to decrease you?
So pixels don't change their size. They are what they are. A couple of lectures ago, I talked about trying basically a conceptual thought to think of your pixels as changing size when your field of view changes perhaps and they stretch out or not. They don't really do any of that, okay? What happens is the computer, much like we're talking about now, will act upon the matrix in different ways. It'll look more closely at individual pixels, or it will look at groups of pixels. And that change between the two is what is represented when you change your field of view or magnify the image or something to that effect. Right? It's not that they actually change or stretch out or compress. What happens is you have, so to give you an example, you have, let's say, 10 pixels that make up a box. You can, and they have different brightness levels. You can change those brightness levels 10 pixels at a time, or 1 or 2 pixels at a time, and it'll change a lot of different things, right? It'll change whether it looks grainy, or whether it looks smoother, or whether the image looks bigger or smaller, right? It's all about changing the grayscale. So here's our summary before we get to a few other items. Right? Spatial domain is by location, very specific rows, columns, identifying all the pixels in your matrix and where they are, possibly doing an operation that's point by point, possibly doing an operation by area, or possibly doing global changes like flipping and turning. In the intensity domain, it's still based on understanding where your pixels are, but it's looking at them from a different perspective. It's looking at them from an intensity brightness level. And this, for example, is where your initial histogram is created. It's also involved in the histogram that's based on the lookup table from the procedure that you chose. And we'll see an example of that a little bit later on. The last one, which is trying to alter the image and process the image, is based on the size of objects. Initially, when you think about it, it's related to knowing where the pixels are and identifying areas that have the same brightness levels. I mean, how else can the computer figure out, an object like the joint in between two phalanges, right? Probably because it realizes that this set of pixels, probably a few hundred of them, because remember, there's thousands of pixels per inch, right? So there's probably thousands of pixels, just on a 10 by 12 that make up just one of the joints in between your first and second phalange. That's going to have a much different pixel brightness level than the surrounding soft tissue. And by doing so, if we stick with this example, we can see that that particular area is rather small compared to the surrounding, what's around the joint. And then break that into frequencies. By the way, the frequency domain is most frequently used in MRI because we're dealing with radio frequencies and magnetic fields that come in wavelengths and frequencies. And this we talked about, so I'm not going to spend much time on it, but in the intensity domain, this is where you have gradation processing, right? When you change your contrast and you're going from one particular curve to another, again, it's based on the steepness level of that curve and how many grayscales are going to be part of the calculation, right? I talked about walking through the woods, but it's really, is the computer going to kind of try to look at more gray or try to look at less gray, and then manifest the image with a different scale of contrast. Again, still the same number of pixels, they're just changing brightness levels. They don't stretch or anything like that. We're going to see this again in a second. So how might this work? So imagine you have lookup table A and lookup table B. And they each represent a different type of contrast. We have a medium contrast and a high contrast. And the assumption is that the column to the left that's not here was your initial image. And now you want to change A or B. So A actually represents curve A. B represents lookup table B. What do you notice about these? So take a look at the input columns.
The same.
So they're the same. So the theory here, now imagine that this number is not infinite, but much, much larger than what it's describing. These are, so there's probably a lot more different pixel brightness levels. Now, the outputs are different, correct? What's different about them? You can't look at any one. You have to kind of see what's going on with A versus B.
The bigger jumps from one.
Yeah, there's a bigger jump. If you look at the contrast in A, we go from 192 to 304, but there's a lot of 200 stuff. Now, if these are grayscales, then we can say that, 216, not that far away from 224, not that far away from 32, 40, and 48, those grayscales are close in color, grayness, however you want to say it.
So it's a long frame.
So it's a longer scale, okay? That's going to represent this image over here, right? A longer scale, more gray. Not necessarily bad, although it looks bad in this image. On the right side, we're making use of numbers that are linked to different grayscales, but because they're so far apart, so this one not only starts at 0 and has a lot of lower numbers in the double digits versus triple, and then going up to 448 versus 300 and such, we have a lot more differences in the actual brightness level of each of those grayscales. So this is going to represent a shorter scale image, right? It's going to represent B, which is also steeper, and it would then be representative of something like what you see over here on the right side, a shorter scale, a higher contrast. Questions? This, you might imagine these output numbers actually changing as you're moving your mouse and windowing the image. Actually changing. Really fast, I guess. And wherever you stop, it freezes for a moment. If that's where you leave it, that's where it stays. So when you're in clinic, think about all that's happening in those 1 or 2 seconds, which is like 1 to 2,000 milliseconds, or 10,000 to 20,000 microseconds. So it's a lot of time. So the computer does a lot of stuff in what we perceive as a very short period of time, just a few seconds. And this is just sort of another example of you moving from one scale of contrast to another. So I'm not going to focus on this. I want to move on to a couple of other items that are terms that affect the contrast of the image. So the next few slides are based mostly on contrast. So there's a term known as the gamma. And you can see there's a lot of gamma curves here. Long story short, what you need to know from here is that as the gamma or gamma, if you want to say it that way, I don't care, it's a multiple choice exam, the contrast goes up when the gamma goes up. And high contrast in this case means short scale. So based on these images, if we take the two extremes, A versus D, A is an image that is kind of washed out, low contrast, where D, it's more black and white, jumps out at you more. I don't particularly like D, it looks a little bit darker to me. Might be too high contrast. Whether you like C or B is kind of judgmental, but I think A and D are the two extremes in this example. Now, these curves are all based on lots of mathematical algorithms and lots of people getting paid good money to do math equations, I suppose. That could be in your future one day. Maybe not. A lot more math than MA 1275, that's for sure. But what's interesting is that they're proprietary. Different manufacturers hide the research that they do to make this stuff work. Life was a little bit easier. Sure, there were different brands of fixer and different brands of developer, but it was pretty much the same chemicals. When I had this class pre-digital, we talked all about the different components just within the fixer and the developer and the chemical names. But we didn't say that one company used one chemical and one company used a different. They were all the same for the most part. I suppose it's kind of like Coke isn't giving their recipe out to Pepsi and vice versa, right? It's all proprietary. Yet the ingredients are on it. High fructose corn syrup. So this is how they distinguish themselves, right? And I'm sure maybe we can have a radiologist come visit us one day, or I can find a blog about this. I'm sure there are radiologists that are just swear by the Fuji system versus the Konica system. Just provides higher contrast or better image for whatever reason. And they say this while the equipment remained the same, right? It's just all on the back end. Not that you switched equipment. So higher gamma, higher contrast. Another activity that helps us visualize an image and overall improves the resolution of the image, as well as potentially saves memory and computational time on the computer itself, is what's known as dynamic range compression, or DRC. Right? It also comes under the title of equalization. And as you'll see on the next slide, it's also related to grayscale truncation. So all three of those go together. So on the left, we have a couple of terms here that you should be familiar with, just to refresh your memory. The dynamic range, sitting in the correct spot here, it's above the bit depth because it's more macro. It's the potential grayscales that your pixels can have or that you can attribute to based on the entire system, right? The hardware, the software, the tube, the computer, everything. Whereas bit depth is only concerning, for the most part, the electronics behind the computer system and the monitors themselves, right? The bit depth is always 2 to the power of the bit depth stated. So 2 to the 8th power, the 8 is a bit depth of 8, would represent 256 grayscales. We talked about how many grayscales we can perceive. Not that many. So while you can have the potential of showing 4,000 or 5,000 different grayscales, if you looked at that you would just be able to see, well, it's darker on this side and lighter on that side. You wouldn't really be able to count that many. You can probably count maybe 30 or 40, where you can maybe draw some lines in between this like gradient of grayscales. So the computer knows that and wants to make the image a little bit better. So it has a process that it goes through known as dynamic range compression, which will attempt to take the whitest grayscales and the darkest grayscales and make them all one scale. In other words, the really, really bright grayscales just become all one bright level, and the really, really dark grayscales, which are technically different darker grayscales, are made all one dark grayscale. So it cuts off the ends. That's better for the computer. It doesn't have to memorize as much. Technically, it's faster because it's looking at things from an area perspective versus a pixel by point pixel basis. And you can save some computer power by doing this, but if you do too much of it, you end up with C. But let's back up. A is representing no DRC, right? No dynamic range compression. It's the full spectrum, basically, all the grayscales, right? B is showing that you can clip and save some of that data. So clipping data at first mention sounds bad, right? But in this case, it's not, right? Because we're clipping things that your brain can't perceive anyway, and at the same time, we're saving memory for the computer. And think about it, each image ultimately is a certain number of megabytes, which we're not going to get into all of that. But storage, even though it seems endless nowadays, is not, right? And hospitals have to pay for this twice because you have to back up everything. So B clips the data a little bit, and you can still change the level. You can still darken it. You can still lighten it. Even though you've taken away some of those potential grayscales. And C shows you what happens if you actually do too much of this. If you really split it in half, at an extreme example, if you make all the brightest, not just that, but even some of the lighter grays, all one bright white level, and all the darker ones, all one dark, then you get just two contrasts. I mean, you get super high contrast, just black and white. So that's too much compression. The next slide shows you what happens when you don't do too much, right? When you do what is good for the computer and good for us. So what is good for the computer and for processing is we're taking some of these lighter densities or intensities on the left and removing them. The pixels don't disappear. We're just not going to illustrate pixels that have the whitest levels. And the same thing on the right side. If you want to use a term that we used in the past class, past a certain threshold, we're getting rid of this. And you can see, one, we're going to save on computer technology, right? Processing time, memory, storage. But more importantly, we get an image that actually looks better, right? Our contrast on the right side is a little bit higher in that we can now make out more anatomy. I don't know if you could see it back there, but, I won't read this word for word, but essentially what it's saying is that you can now see some of the vertebra behind the shadow of the heart here on the right side compared to the left. You could also see some of the soft tissue in terms of the lung parenchyma over here that you can't really see over here. You just see a little bit here and a little bit over here, right? So we actually end up bringing out some of the details in the image that if we would have stuck with A and kept these darkest levels, then a lot of the soft tissue just would have been too dark to distinguish from each other. So equalization, grayscale, truncation, dynamic range compression, all that stuff is a win-win. We save on memory and faster computer stuff, and we make our image better. Not too many win-wins in my class. Usually it's like something's a trade-off. So I get happy. Thank you, Fuji Medical Systems from Stamford, Connecticut. And that about does it for us. So we have extra time, so I'll take any questions you have. And really the reason we have extra time is because a couple years ago, when I had part 1 and part 2 in the same amount of minutes, it was not easy. So questions? Yes, Ken.
How is this different from the pre-processing, like the rescale pre-processing?
See, yeah, that's, it's not much different.
So
I know you, I know you want to kind of draw a line in the sand and you want to say, you know, to the left, that's all pre-processing. To the right, but post-processing is a lot of pre-processing steps redone at a later time. So this is sometimes done when you change your window, which is you know, considered post-processing technically when you're windowing. But some of this is done when that image is switching, like in the DR room, when you see that washed out gray image that's then converted. It's a whole number of steps. And remember, you know, these are processes that happen in slightly different ways depending on the manufacturer. Some of these processes are used one at a time or in conjunction. So it's not necessarily just point processing. Sometimes you're using spatial and frequency. So there's a lot of different ways that these things are done. And it's really come down to a manufacturer specific type of procedure, which is why none of them at whatever conventions they go to like to discuss exactly what they're doing at dinner time. Yes?
I want to know what exactly is the lookup table and how is this necessary applied to us?
Okay, so the question is, what is the lookup table? The lookup table is representative of another histogram. It's another mapping of what the pixel brightness level should be optimally for a particular exam. So there's a lot of lookup tables. Right? And things get more dynamic when you don't agree with the image that comes out, and then you want to change the contrast, which is what you are essentially doing here. You're now, in a way, writing up a new lookup table. Now imagine that you've changed from A to B and you like B. On your fancy monitor, you can create B as a preset. So the radiologist gets another hand, presses a preset, and then up comes a new contrast. And then they can see multiple images, the same image with different contrast levels. We do this in MRI and CT all the time, right? In MRI, you might see a T1, a T2, and a proton density weighted image, all in a separate window, same slice, same anatomy, different contrast for each one, right? So the lookup table is grayscale values. Each grayscale has a number, right? Usually higher numbers are brighter, lower numbers are darker. And you're changing not only which ones appear, but how often, right? Because there's a difference between taking out and truncating versus taking what you have and stretching it out or making it smaller. Truncating just gets rid of stuff, just chops it off from either end. So the lookup tables are based on what the manufacturer thinks is the optimal image. So how do you think they created theirs? They basically took radiographs digitally, they had the components, and then people thought that this little area should be darker, this little area should be lighter. Let's make our new histogram more, so in a sense, I can only picture them doing something similar to this, windowing it and saying, this is the way, and they have 5 radiologists to look at it to say, yeah, we agree, we like it that way. And then that becomes the new histogram. Right, the new lookup table histogram. Anything else? No? Midterm study? Yes, Ken.
When I think of pixelation, I'm thinking of like if you go from 16-bit to 8-bit, it gets more pixelated. But I don't understand how your spatial resolution would go up if it looks more blurry.
So, all right. Are you talking about bit depth when you say 8 versus 16? So let's do the math. Since this is on the video, you can decide to watch this for yourself if you want. If we do if we do 2 to the power of 8, we have 256. 2 to the power of 16. So we're jumping from 256 to 65,000 potential grayscales. It's a big difference. Your question, again, is what makes it grainy or blurry?
The information is the same. The amount of information stays the same.
Okay, so I have to admit it's difficult to comprehend. You have a limited number of pixels. You have a lot of them, but you have a limited number, and they don't go away and they don't change size. We talked about that. All a pixel can do is change its value. And at certain times, based on those pixel grayscale values for each one within groups, sometimes your image looks noisier and more pixelated, and sometimes it doesn't. It's not like the screen gets messed up, right? It's the representation, and a lot of it goes back to, if you don't have enough X-rays, you don't provide enough signal to be processed, and the computer gets confused. I know I'm not perfectly answering your question. It's hard to say, how do the pixel values change that make it look noisy versus smoother? They do, right? They change on sort of an area level.
Is it somehow related to the frequency?
Well, frequency of
We studied before the for the special resolution. Frequency of the special resolution.
Overlapping?
Yeah. When it's overlapping.
right, yeah. When there's too much overlap, a decision gets made to attribute a certain brightness level to a set of pixels, and that might end up being incorrect and not the best choice. And that's probably manifested as noise. Yeah. Okay, guys, watch my videos.
For the midterm.
For the midterm, yes.
Is everything but today? The chapters.
And whatever the chapter was on